In the first second after the Big Bang, our universe was an almost inconceivably hot and dense soup of primordial particles. Over the next 3 minutes, as the cosmos expanded and cooled, the nuclei of helium and other very light elements began to form. Fast forward 400,000 years, and the universe was cold enough for the first atoms to appear. When the universe was about 100 million years old, conditions were finally right for the emergence of the first stars. These giant fireballs of mostly hydrogen and helium were as yet uncontaminated by heavier elements like modern-day stars, and thus possessed significantly different properties. Larger and brighter than today's stars, these first suns coalesced in protogalaxies, clusters of gas that clung to vast invisible scaffolds of dark matter. Gravity guided the subsequent interactions between these protogalaxies, which eventually merged to form larger galaxies. This process of becoming of the early universe's chaos, giving way to the more orderly cosmos we know today, is thought to have taken about 1 billion years. When we look at these early galaxies, they look very different than the newer and closer galaxies. The closer an object, the more blue-shifted its light is, and the further the object, the more red-shifted its light should be. Let me explain. As light from a very distant galaxy travels across the cosmic abyss, it is stretched by the expansion of the universe, a broadening of wavelengths, known as redshift. The higher the redshift value, the more stretching the light has experienced, and thus the more distant its source galaxy will be. That means the primordial galaxies should not only be redshifted, but have a significant redshift value. Well, we didn't have the means to look at them until the James Webb Space Telescope was launched, and guess what? Once again, it is toying with our understanding of the cosmos. Welcome to Star Extreme. There is a little space for everyone here. Now that we have a powerful lens pointed toward the deepest regions of the universe, our definition of surprise has slightly altered when it comes to astronomy images. It's no longer surprising, really, when NASA's James Webb Space Telescope reveals yet another brilliant, ancient piece of the cosmos. At this point, we know to expect nothing less from the trailblazing machine. However, it is kind of getting a little difficult to keep up with the telescope, as it is reshaping our understanding of galaxy formation and evolution and breaking the record for the oldest known galaxy. It turns out some of these early galaxies may challenge existing models of galaxy evolution and their dust. These galaxies discovered by Webb are very bright, metal-enriched, and massive. One of them is Glass C13, which dates back to just 300 million years after the Big Bang, older than any galaxy ever seen before. These galaxies, as we have now found out, are so massive that their stellar mass ranges from 0.1 billion to 5 billion solar masses. Such massive, well-formed galaxies should not exist in the early universe, as per our cosmological models. Then, what is going on here? Normally, a galaxy with these qualities would have a lot of dust, and would therefore undergo significant reddening of light. But these don't. So, where did all the dust go? To understand this, we will need a brief refresher. Cosmic dust, consisting of particles less than a few millimeters in diameter, is a universal phenomenon and an important component in the history of all planetary and star systems. Dust and gas make up the molecular clouds in which planetary systems originate, collapsing to form stars and their protoplanetary disks. However, they obscure visible light from reaching us from cosmic objects behind them, making the universe appear dark and inaccessible. But there is a bright side to them. The dust converts the trapped starlight it had absorbed into light at longer wavelengths, which we can observe when we turn our infrared telescopes towards them. And that's why, while studying distant objects, we have to consider their dust attenuation, which is how their dust impact the general spectrum of light coming from them. And when we correctly determine that, we can then also determine the stellar mass or population of that galaxy. Now, since we are done with the refresher, let's go back to the blue monsters that the James Webb Space Telescope has discovered in the early universe. How are they so massive and without dust is a puzzle that scientists are trying to figure out. Like we mentioned before, such well-formed galaxies should not have been present so early into the life of the universe. Their sheer size rule out the possibility of them not being obscured by dust. Massive stars and supernovae have been major dust factories ever since the first generations of stars formed several 100 million years after the Big Bang. And only once dust is available, the second-generation stars form much more quickly and efficiently, which tells us that there must be a lot of cosmic dust early on. But these blue monsters don't. So, where did all the dust go? Scientists proposed two explanations for how you could get a bright, enriched galaxy without a lot of apparent dust. First, dust ejection theory. For this theory to work, dust ejection has to be effective at removing dust. That is, the rate of dust ejection must be higher than the rate of dust production. And although the dust ejection is a plausible theory for the apparent lack of dust in bright blue galaxies observed by the James Webb Space Telescope, scientists note that some galaxies at high redshifts may not meet the physical criteria for dust ejection and could instead fall into the dust accumulation regime. The second theory is that maybe the UV emission mostly comes from the diffuse interstellar medium, while the dust is concentrated largely in infrared-emitting, giant molecular clouds. With this assumption, the authors can make predictions for a lower limit on the flux in the far infrared, which would originate from the dusty molecular clouds. Because of the high redshift of these galaxies, their far infrared continuum emission is redshifted to millimeter bands, observable with ALMA. For the high redshift galaxy, Glass C13, that was observed with both JWST and ALMA, its far infrared flux fell well below the predicted lower limit. Scientists suggest that this result is more consistent with a dust ejection scenario in which the galaxy would be dim in the far infrared due to its lack of dust. Puzzling objects have appeared with Webb observations that may rock existing galaxy formation and evolution models to their very core. But scientists are still figuring out the very nature of these blue monsters, and until we are absolutely certain, we will have to go with theories. Who knows, more observations will reveal more surprises, pushing our cosmic origins farther than we know. What do you guys have to say? Drop in your comments below, and don't forget to subscribe to Star Extreme. There is a little space for everyone here.